With this video, I'm going to try to convince you that yes, we needed yet another video on Gödel's first incompleteness theorem. That's the theorem where he proves there's a true mathematical statement that cannot be proven. I hope to show you that the shorthand description I just gave, the one that's always given, can leave the viewer with a serious misunderstanding of the theorem. Once we go a little beyond that shorthand description, you'll see the word true needs a lot more qualification. And you'll see that it's a good thing the statement in the theorem isn't provable. Because if it was, we'd have no confidence that our proofs are not proving false statements. The incompleteness theorem can best be understood by examining a similar situation that happened almost 2,500 years ago. Euclid, the father of geometry, devised a set of assumptions, called axioms, that he used to prove facts about plane geometry. With his original axioms he could prove many geometric statements, but there were some others that he was sure were true, but couldn't prove. One was the parallel statement. Given an initial line, and a point not on that line, there's only one second line through the point, parallel to the first. Here, line means straight line, infinite in both directions. He wasn't able to prove it, even though it's obviously true. And he needed it to prove many other statements that he believed were true but couldn't prove without it. So he ultimately adopted it as his final axiom. Believe it or not, 2,000 years later, some mathematicians were still trying to prove the parallel statement using just the original axioms. They weren't able to prove it either, but in the process, they discovered two previously unknown geometries, spherical and hyperbolic. These are geometries on a curved surface rather than a flat plane. It turns out that all of Euclid's original axioms are true in these two geometries as well, but the parallel statement is false. Spherical geometry is the geometry of lines and points on a sphere, where a line means great circle. So every line crosses every other line. There are no parallel lines. In modern terminology, we would call plane geometry the standard model of the original axioms, because that's the geometry Euclid was trying to capture with those axioms. And the other two would be called non-standard models. But all three are perfectly valid models of the original axioms because all those axioms are true in all three models. It just so happens that two of them were unintended models, models Euclid didn't know existed. Now we fast forward a couple of hundred years to 1929. 2 years before Gödel proved the incompleteness theorem, he and some other mathematicians proved a relationship between truth and provability. If a statement is provable, then it's true in all models. And if it's true in all models, it's provable. So at that point in history, we learned why no one could find a proof of Euclid's parallel statement from the original axioms. It's not provable because it's not true in all models. And now we come full circle back to the first incompleteness theorem. And we switch from geometry to arithmetic. In 1889, Giuseppe Peano finalized a set of axioms for basic arithmetic. These axioms provide much of the basis for a major branch of mathematics, number theory. It's theorems from number theory that provide a way to prevent your credit card number from being stolen when it's sent across the internet. And in 1931, Gödel proved his first incompleteness theorem. In that theorem, he constructed a statement of arithmetic. I'll call it G, Gödel's statement. He proved there is no formal proof of G from the axioms. But using everyday informal reasoning, we can see that it's true. We also know from the work done 2 years earlier about truth and provability, since G isn't provable, it's not true in all models. So how do we make sense of these seemingly contradictory facts? Well, it turns out that, just like there were unintended models of the geometry axioms, there are also unintended models of the arithmetic axioms. Models no one knew existed when they were formulated. The standard model is the one we learned in grade school. It consists of the standard numbers 0, 1, 2, 3 and so on, and ordinary addition and multiplication. But it turns out there are also non-standard models, in fact many different ones. They all have the standard numbers, along with addition and multiplication. But they also have infinitely many additional non-standard numbers, all greater than any of the standard ones. And yes, they're all perfectly valid models of arithmetic, because they satisfy all of Peano's axioms. Now what about Gödel's statement G in the incompleteness theorem? That's supposedly true but not provable. It turns out G is true in the standard model, but false in some of the non-standard models. So because it's not true in all models, it's not provable. And here's a very important point. It's a good thing statement G isn't provable. Because if it was, we would be proving something that's false for those other perfectly valid models. And if we could prove a false statement for those models, then presumably we could prove a false statement for the standard model. So if G was provable, we couldn't trust any of our proofs. Now, after you think about this for a while, you might wonder, why can't we add an axiom or two, and eliminate the non-standard numbers, and with them the non-standard models? Then we would have only one model, the standard model, in which G is true, and therefore provable because it's true in all models. That's an excellent question. Here's what happens when we try that. In order to avoid the inherent ambiguity of natural languages, mathematics uses a precise formal language to express axioms and formal proofs. It's called first-order logic. It turns out that this formal language, while possessing many desirable properties as a proof system, is not expressive enough to formulate axioms that eliminate those non-standard numbers. Well, you might ask, why doesn't mathematics use a different, more expressive formal language? After all, logicians study many different types of such languages. As you might expect, that's been investigated, and very briefly, here's the result. Second-order logic is a more expressive alternative, and really the only other alternative rich enough for mathematics. Here's how they compare. Second-order logic is expressive enough to eliminate all those non-standard models, leaving only the standard model. So with second-order logic, Gödel's statement is true in all models, since there's only one. And yet it turns out that it's still not provable. Why? Because the strong relationship between truth and provability that exists for first-order logic doesn't hold for second-order logic. With second-order logic, a statement can be true in all models, even when there's only one, but still not be provable. That's a proof system with a serious deficiency. And that's a deal-breaker for using second-order logic as the formal language for mathematics. With first-order logic, if a statement isn't provable, it shouldn't be. And we know why. Because there's a model in which it's false. But if it's true in all models, we want a proof system that can prove it, and first-order logic guarantees us that it can. That's why mathematics has chosen to stick with first-order logic. So that's the backstory on Gödel's first incompleteness theorem. I hope you see why I thought yet another video was needed on this. And who knows, this may have been the very thing Kurt Gödel and Albert Einstein were discussing as they walked home that day, after a hard day's work at the Institute for Advanced Study at Princeton. Thanks for watching, and if you feel you can recommend this video to other viewers, please click the thumbs up button below. I'd also be interested in hearing your comments.